Our speaker today is Jon Zink. He'll be talking about assessing galactic influences on planet formation with exoplanet demographics. Jon is currently a NASA Hubble Fellow at Caltech, which is why he's gotten up super early to give us this talk this morning. So I really appreciate that, Jon. He also originally attended UCLA for his BS, and then I believe he worked on Kepler and K2 mission data for his PhD work before he moved to Caltech. So I'll let you go ahead, Jon, and you can tell us about the cool stuff you've been working on.
Great, thanks. Hi, everyone. Thanks for having me today. It's a real honor to be presenting to this group of people, talking about my work. Okay, so let's get started. So there's really three topics I want to talk about today. The first one is going to be our Scaling K2 project, where we're building a uniform catalog of planets to start doing demographics work on the K2 mission. The second part of my talk is assessing that catalog and looking at some of our early findings, how they compare with the Kepler mission. And the final part is going to be talking about some new information we're learning from K2 that's really allowing us to expand our understanding of planet formation. So why do we care about demographics? Well, the big question that I'm hoping to answer is figuring out how unique is our solar system. In order for us to do that, we really have to answer two sub-questions that are buried within that. We need to understand our origin, how do planets form, and we need to understand our history. How do orbits evolve over time? And the reason demographics plays into this is because with demographics, we get all of these different snapshots of planet formation and orbital evolution in time. And our goal as scientists here are to put these images together to form a cohesive story of how planets form and evolve over time. So hopefully by taking all these snapshots, we can kind of line them up in a way that allows us to understand our origin story. So the main focus of demographics has really been based around this Kepler mission. The Kepler mission, as probably everyone here knows, stared at one patch of the sky for 4 years, collecting continuous photometry. This photometry enabled us to find these really exciting transiting planets, which occurs when a planet moves in front of the star, blocking some of the light. From these planets, we can learn something about the orbital period and the radius of the planet. The Kepler mission really found an abundant number of short period planets. So in this plot I'm showing here, that we have planetary radius along the y-axis and orbital period around the x-axis. So all these red dots are just planet candidates found by Kepler. And I also put the solar system planets here for reference. Mercury, Venus, Earth, you can see that. So what's really interesting is just by looking at this plot by eye, you see that most of the planets found by Kepler are in a parameter space that is very different from the planets we see in our own solar system. This is quite surprising. Now, after you think about this for a moment, you have to ask yourself, okay, well, that's great. We found all of these planets that are very unique from what we see in our own solar system. But is this sample representative? Maybe there's some biases here that are contributing to this weird population that we're observing. And to really account for that, we have to think about the selection effects that are kind of inherent in this sample. And so there's two big things we need to think about. The first one is understanding whether the planet is transiting or not. So, clearly for a transiting planet, you need the orbits to line up with our line of sight so that it blocks some of the light from the star. And this can be calculated analytically. It comes down to a pretty simple formula. The transit probability is essentially the stellar radius divided by the planet's orbital radius. That gives you some probability of the planet actually transiting. The second effect is much more difficult to understand, and that's, can we actually detect the transit? So assuming that it does line up nicely and block some of the light from the star, are we actually going to be able to detect it with our instruments? This is not quite as straightforward. There's not a nice analytic function for this. This is detector dependent. There's all kinds of issues in here. But the Kepler mission made this a little more simple because they developed this fully automated pipeline, removing the human element from the detection, the detection method. And this is really important. By fully automating the pipeline from front to back, from raw data all the way to candidacy, this allows us to really get a good handle on what the inherent biases are in our sample. And so this was work done by the Kepler team. The RoboVetter was kind of the final piece to this puzzle. And this took the last part where you find the dips, and then you have to determine if the dip is real or a false positive. And the RoboVetter used all this suite of metrics that kind of helped identify whether these dips were authentic or not. So once we have this fully automated pipeline, what you can do then is you can inject these artificial signals into the photometry. By injecting these artificial transits, you then can pass them through the pipeline and see what you get out the other end. So this plot on the left is kind of showing what came out of the Kepler pipeline when they did these injection tests. So on the x-axis, we have the signal to noise ratio, and on the y-axis, it's the recovery fraction. So looking at this, you can see at really low signal to noise, pretty much nothing was recovered. And then at really high signal to noise, on order of like 20, you see that almost all of the planets were recovered, all the artificial injections. And then there's this whole in the middle region. Now, this idea of high signal to noise, you find everything, low signal to noise, you find nothing. This is really not surprising. I think everyone probably would have expected that just naively. But what's really important about this plot is that it allows us to quantify this region in between. And that's really important for the Kepler mission because about 50% of the planets exist right in this signal to noise region. So this is a really important part of the parameter space that we're sampling. And this was work headed up by Jesse Christensen, and many others had kind of replicated different studies like Pettigura et al. But this is a really important process or feature of the Kepler sample, that we have this completeness mapping ability. And what that allows us to do is now correct the sample and find out what the underlying planet population really looks like. So on the right, I'm just kind of illustrating how that can be done. So this is just a histogram of raw occurrence as a function of planet size here in gray. So there's a bunch of really small planets, as we saw in the previous plot. And what we can do is take this completeness mapping and correct this for the number of planets we're missing. And so what you can see is when you correct for that, there's even more small planets than what was detected by Kepler based on this completeness mapping. And you can see there's not so many added in the larger region because we're mostly complete in that part of parameter space. So what does that look like when we come back to our plot over here? So what that means is that there's a lot more small short period planets that we're not detecting, which means that it's really interesting that we're not finding, or we're not seeing many of these in our own solar system, right? Mercury seems to be way out here, yet there's a ton of planets in most other systems that are at shorter periods and sometimes even much bigger. Now that may indicate that our solar system is quite unique, but we still need to do more digging, because you'll notice this region of parameter space over here where most of the solar system planets kind of lie is not really well probed by the Kepler mission. We just have really low completeness over here, so it's hard for us to say much about what's going on. We can certainly extrapolate, but at the end of the day, that is still an extrapolation. So there's a lot more work to be done with exoplanet demographics, certainly. But the Kepler mission was not the end-all be-all of demographics. Remembering that what happened at the end of Kepler is that 2 of the reaction wheels failed, rendering the pointing stability unable to point at a single location for a long period of time. But the K2 mission was born out of that malfunction. And there was a lot of really good science to be done with K2. And so that brings me to kind of the first point in my talk, and that's the Scaling K2 project. So why am I really excited about K2? K2 is really exciting because it probed different regions of the galactic ecliptic, or probed different regions of the ecliptic, and kind of looked at different parts of galactic latitude. You know, we have a wider range of stellar ages, stellar masses, and stellar metallicity. The Kepler field was selected because most of the stars in there are FGK and have like solar-like metallicity and things like that. So if we want to think about, you know, wider stellar parameter space, the K2 mission is really exciting. We have a ton more M dwarfs, things like that. And we can really start to hone in on how these different aspects of the stellar features play into planet formation. But it wasn't all just super easy. We couldn't just say like, okay, let's run the same Kepler pipeline through and, you know, assess the demographics, so forth. Because there were different systematics involved with K2. One of them that was really problematic is every 6 hours, there's this pointing issue where the telescope needs to be realigned, and it causes a lot of these artifacts in the photometry. So on the left here, I'm just showing one of these artifacts. It's just kind of this weird dip-like feature. And you can see that, you know, if you were to run some kind of BLS or TLS algorithm through, it's probably going to pick this up, and it looks like some kind of transit signal to, you know, a naive computer. But obviously with visual inspection, people can pick this out and say, okay, that's clearly not a transit, it's some kind of artifact. And then alternatively, the guy on the right here is actually a real transit. And, you know, your TLS or BLS algorithm searching for these dips would definitely identify something like this. But you still needed a person to go through and check whether this was a real signal or not. So pretty much for a while, after the K2 mission ended, all the planets found through K2 required some amount of visual inspection. And that really makes it difficult for demographics to be carried out. But nonetheless, there were about 1,000 K2 planets identified through visual inspection. So again, you can see there's a large number of short period small planets. You'll notice that I only have Mercury plotted on this plot. And that's because K2 doesn't have the baseline that Kepler did. So Kepler stared at one field for 4 years. K2 only looked at each field for about 80 days. So we don't really have the ability to probe those longer period ranges that we were with Kepler, but we can still learn a lot of cool science about these shorter period planets where we seem to see a large abundance. So all that said, we talked about K2. It seems like at this point, visual inspection was the way to go. But if we really want to do demographics, we have to take this to the next step. And that's where the Scaling K2 team came in. So this team is made up of a bunch of great scientists, really headed up by Jesse Christensen, Kevin Hartery-Allman, and myself. We're really trying to develop K2 into this demographic mission and carry out some really exciting science with that. So in order for us to do that, we really needed to think back and kind of learn some lessons from the Kepler mission. How can we build a pipeline that is fully automated? And this was a big part of my PhD, was building this fully automated pipeline for K2. And really what was necessary was this additional vetting metric on the back end. And so I developed a suite of vetting metrics that kind of mimicked the human vetting process and kind of went up and above what the Kepler RoboVetter had done. And so I took a lot of the lessons learned from RoboVetter and then added a bunch of new metrics that were very specific for K2 that could identify these weird, you know, artificial dips that weren't necessarily transits by any means. And so by developing this pipeline, we were able to automate the transit detection process for K2. And what we found is a catalog of 747 unique candidates. We had 51 multi-planet systems and over 300 brand new candidates. So this is really exciting. And while that's all great, new planets are always really exciting. What we're most excited about is the fact that we can make this completeness map that you're seeing here. And so we have this homogeneous set of planets, but now we also have an understanding of how complete is this sample. So a few things to note is that you see we found about 300 brand new candidates, and we found 700 planet candidates in total. So you might be asking yourself, well, it seems like we're missing quite a few of the known planets. And that's absolutely true. But remember, our goal here is not necessarily to find every single possible planet. Our goal here is to create a homogeneous sample that we have a good measurement of the underlying completeness. So the cost of doing business here in K2 world is that we're going to lose some planets in order to gain completeness. And that's just because the photometry is so much more noisy than Kepler. It's difficult to get every single planet and have good completeness and high reliability in your sample. So before we dig in too deep into the more demographic level of K2, I just want to talk about a few unique planets that we found in our sample. So these are new planets that have recently been validated by Jesse. And one of them is K2339b. This planet is really interesting because you'll notice it's kind of in this region of parameter space where there's not a lot of other planets. So this is a hot sub-Saturn-like planet. And this region here looks like maybe there's some completeness issues, but this is a very complete region of parameter space. We should be finding most of these planets here. So this apparent dearth is some kind of indication that there's some formation mechanism here causing planets to either not be formed or lose their atmospheres and be pushed down. Maybe they're being tidally stripped. Something is happening here in the formation process that doesn't allow planets to really live here. So finding one more in this really rare parameter space could be really influential in helping us solve the mystery of what's causing this lack of planets here. Another interesting planet is K2408. So this is a super Earth, a low metallicity super Earth. So there's a lot of work that I'm going to talk about later on in this talk, thinking about the correlation with planet occurrence and metallicity. And finding planets at really low metallicity helps us kind of move that lever arm. There's not a lot of planets over here. So in the region where there's low occurrence, a few extra planets can really help us constrain the metallicity trend. And then finally, one of the big systems we found was a 5-planet near resonant chain system. So these plots are a little complex, but essentially what they're saying is that if the eccentricity is bumped up just a little bit for any one of these planets, it's most likely going to put them in a 5-planet resonant chain. And this appears to be the closest analog to TRAPPIST-1 we have so far, because this is a mid-M dwarf, high multiplicity mid-M dwarf with a lot of short period planets. So definitely some exciting science to be done on this system as well. Hopefully we'll get some RV follow-up in the near future and be able to kind of reduce this uncertainty in eccentricity space. Okay, so talked about the Scaling K2 project. We now have a homogeneous catalog of planets. The next step is we want to start doing some demographics on this catalog and think about what exciting science we want to carry out now that we have our uniform sample. So let's just kind of go over exoplanet demographics as they stand from the standpoint of Kepler. So I'm going to focus on FGK stars today because a lot of this work is comparative to Kepler. And as I mentioned previously, the Kepler field was selected because of its overabundance of FGK stars. So comparatively, to make sure everything's apples to apples, we're going to focus on FGK dwarfs with K2 as well. But what did we learn from Kepler? One of the big things we found were that there appears to be these 4 different classes of planets that have these interesting breaks in occurrence that indicate maybe they have unique formation origins. The first one being the super-Earths, the 1 to 1.8 Earth radii. Next being the sub-Neptunes, 1.8 to 4 Earth radii. The sub-Saturns, 4 to 8, and then the Jupiters, 8 to 20 Earth radii. So looking at the demographics of these different classes of planets, we'll see some interesting trends. So here I'm just plotting planet occurrence as a function of period here. And this is for the Kepler sample. And what we learned from Kepler is that there's a lot more super-Earths and sub-Neptunes than there are Jupiters and sub-Saturns at these shorter period ranges, which is interesting. It may give us some indication of the disk mass in this short period range, maybe tells us something about migration rates, and so forth. But overall, there's more super-Earths and sub-Neptunes at shorter periods than there are Jupiters and sub-Saturns when accounting for completeness and other selection effects. Now, digging in a little deeper, we'll notice there's a few kinks in here. So there appears to be a kink in the super-Earths and sub-Neptunes. Yeah, roughly 7 to 10-ish days. It appears, or we believe at this point, that this lower occurrence in the shorter period range indicates that there's some inner disk edge here. And so planets are either getting truncated at this inner disk edge, or they're just unable to form down here in these shorter periods. The story is a little more complex for the sub-Neptunes because there's photoevaporation effects that also could reduce the occurrence over here. But overall, it appears that there's some kind of break in the disk at roughly 7 to 10 days. For the Jupiters, we'll see there's this really famous 3-day pileup. So you'll notice that it's a slow trend up to 3 and then kind of slowly moves back down. If we extended this further, it actually starts to pick back up. This 3-day pileup is famous because it seems to indicate some high eccentricity migration effects are occurring here. So at 3 days, what is expected is that that's the kind of the limit to where these planets can get dragged into. And so that indicates some kind of unique migration evolution over time for the Jupiters, these hot Jupiters. And then this dearth of planets at short periods for the sub-Saturns maybe indicates some kind of tidal stripping. You get too close to the star, you get stripped away. So these are some interesting demographic features found with the Kepler mission. Now, what about K2? So what does it look like when we lay our results from K2 on top of this? Well, just based on looking at it really quickly, everything seems to line up pretty nicely. We see the same 3-day pileup roughly with K2, same general trends for the sub-Saturns, sub-Neptunes. It seems to line up pretty well for the super-Earth. There's some deviation over in this region of parameter space. I wouldn't take too much from that. It's still within like a 2 sigma difference here. This is also a portion of parameter space that's very incomplete for K2. It's hard to find these longer period, smaller planets. So maybe you wouldn't take too much from that. But overall, it seems like most of these trends line up pretty well with K2 and Kepler. So what does that mean? So when we take a step back and think about that, that has really broad implications. That means that pretty much anywhere we look in the local galaxy, it appears that we're finding roughly the same number of planets. And that's really exciting because a lot of what the work done with Kepler, people like to assume that maybe that's true for all regions of the local galaxy, but we really didn't know that to be true until we really dived into the K2 data set. It's very possible that some of these strange occurrence features may be specific to this one field. But now with K2, we're able to say, no, this appears to be a general trend that can be applied to a lot of the local galaxy. So let's dig in on that a little bit more. So generally, it looks like K2 lines up really nicely with Kepler. What about some of these more famous occurrence trends that we've identified with Kepler? How do they appear to line up with K2? So just to highlight a few here, we have here I'm plotting stellar intensity or stellar flux as a function, or sorry, yeah, stellar flux on the x-axis, and then planet size on the y-axis. And there's a few interesting features that pop out of the demographics. One of them, as I previously kind of alluded to, was the sub-Neptune desert, seeming to be a large dearth of planets over here. And another one is the radius valley. So this was a lot of work done by B.J. Fulton et al. To show that there seems to be kind of this divot in planet occurrence as a function of radius right in this region here, kind of separating the sub-Neptunes and the super-Earths. So the expected formation mechanism that may cause both of these features is potentially photoevaporation. So if a planet were to form in either the radius valley or the sub-Neptune desert, the expectation is that photoevaporation, or photons, will hit these atmospheres that are not quite gravitationally bound really tightly and remove them, kind of pushing planets into the super-Earth camp from either the sub-Neptune desert or the radius valley. So yeah, that same effect we believe may be causing the sub-Neptune desert as well. There's some competing theories with core-powered mass loss and so forth that may also produce this same effect, but that work is still, it's still unclear which one of those is the dominant formation mechanism. So great, so this is our completeness map for K2. We see these two interesting demographic features. What does it look like when we lay our K2 sample on top of that? It seems like we find very similar formation mechanisms. So sub-Neptune desert appears right there, and the radius valley seems to line up really nicely as well. So again, what we can say is that K2 is kind of showing us that our Kepler results can be taken to the bank and we can apply them to the local galaxy at large. Some really exciting findings. So moving forward, we've talked about a bunch about K2 and Kepler and how they're the same. I want to start thinking about, well, what's different about K2? What new science can we gain from K2? And so to do that, I want to really dive into this idea of stellar parameters and how they affect planet occurrence. So there's some classic features that have been identified back in the early RV days and been verified with the Kepler sample. The first one being that spectral class, or T effective, is important in planet occurrence. So this is Howard et al. 2012, and Heismolders verified this with the Kepler sample. But basically the idea here is that as you increase the stellar mass, so going from M to F, you'll notice that planet occurrence goes down. This is really counterintuitive because when you think about larger mass stars, you tend to think that they correlate to larger mass disks as well. And so naively, you might think that more massive disks, you're going to get more planets. But we're finding quite the opposite. With these more massive stars, it seems like there's fewer planets. And this is all completeness corrected. So this is not apparent to be some observational effect. It seems like there's something unique here that we don't quite understand yet. So we went and checked this with our K2 sample to make sure that this holds up. And we find very similar trends. So this is stellar, stellar temp here on the x-axis, kind of our proxy for spectral class and stellar mass, because stellar mass is hard to directly measure. And we can see for the super Earths and the sub-Neptunes, we get this nice downward trend as you go to these more massive stars in both scenarios. Also true for the sub-Saturns. It kind of flattens out for the Jovian planets. This might be indicating that this is kind of the saturation point where disk mass is really important. If we extended this downward, we would expect it to kind of turn over here because you're getting into the M dwarfs, where there's just not enough disk material to actually produce these hot Jupiters and so forth. So this might actually, this class of planets might actually follow our expectations of disk mass and planet occurrence. But these other classes kind of are counterintuitive, and there's a lot more work to be done here. We don't have a good understanding yet of why that's occurring. The second stellar parameter that I want to talk about here is metallicity. And so again, early RV work had noted that the hot Jupiters were found mostly around more metal-rich stars. And we think that stellar metallicity is a proxy for the disk metallicity, or how much metallicity existed in the early natal disk that may have caused planets, dust to coagulate and cause planets to form. Work recently by Pettigura et al. Looked at the Kepler sample to see if this was true for transiting planets as well. And you can see for the Jupiters and the sub-Saturns, there's definitely a strong correlation with stellar metallicity and planet occurrence, and a much weaker correlation for the more terrestrial planets, these super Earths and sub-Neptunes. It's not quite as strong. Maybe metallicity isn't quite the determinant that it is for the gas giants. Again, we wanted to verify this with our K2 sample, and we could see that the trends kind of hold up. So for the super Earths, sub-Neptunes, we're finding a pretty flat trend. It flattens out a little bit even more with the K2 sample included. We're still finding strong correlations for the sub-Neptune, or sorry, the sub-Saturns and the Jovian planets. But it seems to be that metallicity may not be the dictator for the super Earths and sub-Neptunes that it is for these gaseous giants. There's a lot in here, and I'm not sure we have a good handle yet on why that might be. One thing that I'm personally interested in thinking about is maybe if iron metallicity is not the important feature here, but maybe alpha elements or silicons, magnesiums, things that we see really commonly in the Earth, for example, might be a stronger predictor of planet occurrence for these more terrestrial planets. But there's a lot of work to be done there on that front. But we can kind of maybe not do this with metallicity quite yet, but we can think about it more with location and see if maybe that's important. And this is some recent work done by Chen et al., 2021. And basically, this is kind of this first idea of thinking about galactic location or location in the galaxy and how it may play into planet occurrence. And so this plot's a little bit challenging to read. Essentially, what this is the probability of being in the thick disk versus the thin disk. And really the big takeaway from this plot is that it appears there is a higher multiplicity in the thin disk planets than there are in the thick disk planets. And so there's really a lot to take away from that, because when we look at kind of our samples, I should note that this is coming from the Kepler sample specifically and using Lamos data to kind of identify whether it's thin, thick disk, and Gaia data as well. But you'll notice that the Kepler sample is pretty bound to the thin disk, which is an alpha poor region or not very alpha element enhanced. Whereas the thick disk region has a lot of alpha element enhancements, which I kind of indicated might be important for these smaller planets to form. And there's some early evidence to suggest that that's true, but we really need a better sample. And fortunately, K2 may be that sample that we've been hoping for, because looking at the K2 sample, you'll see, yes, we get a lot of thin disk stars, but we also probe deeper into the thick disk as well with K2. And this kind of helps us maybe look at these thick disk stars and see if alpha element enhancement is important. So moving forward, I want to just kind of talk about scale height and distance from the galactic midplane, and does that have an impact on planet occurrence? And this is some of the recent work I've been doing with the K2 sample, is kind of diving into this and seeing if we can find any trends as we move away from the midplane. So let's look at each class individual of planets. So for the Jupiters, do we see a trend as we move away from the midplane? So it looks like there is a minor downward trend in planet occurrence. But you kind of have to think back and say, okay, are we actually seeing a trend that is dependent on galactic location, or are we just seeing some effect that's caused by reduced metallicity as you move away from the midplane, or the more massive spectral class that you're seeing as you move away from the midplane due to observational constraints? So for the Jupiters, you'll see that there's definitely, looks like a downward trend in planet occurrence, but most of this can be ascribed to stellar metallicity decreases. So metallicity seems to be the cause of this decrease. We're going up, we're seeing lower metallicity stars. So yes, it's expected that we would see reduced planet occurrence. Now let's go to the sub-Saturns. We do see a downward trend. I will admit this trend is not as clean as the previous one, but it's downward. Now, this one is less metallicity driven and more spectral class driven. So we're just seeing later our more massive stars here in this sample. And as I pointed out, more massive stars tend to have lower planet occurrence. So this downward trend is mostly driven by the fact that we're just looking at more massive stars as we move up the galactic midplane. All right, let's move on to the next class, and that's the sub-Neptunes. So the sub-Neptunes is where it gets really interesting. We see this really strong downward trend. We know metallicity doesn't really play a big effect on the sub-Neptunes, and spectral class certainly plays an effect, but it's not quite enough to explain this downward trend. We need some third parameter, which is scale height dependent, to explain this downward trend. So that's really interesting. As we're moving away from the midplane, we're finding planet occurrence reduces for the sub-Neptunes. This also appears to be true for the super Earths. We're not able to fully describe this trend with metallicity and spectral class. We need some third parameter to kind of compensate for this downward trend. And that's really an interesting finding, because it seems to indicate that as we get away from the midplane, the occurrence of sub-Neptunes and super Earths decreases. And why might this be the case? This is actually a little counterintuitive, because I kind of was alluding that alpha element enhancement may increase sub-Neptunes and super Earths. So it's a little surprising that we're seeing this downward trend. So it's not totally clear yet. We still need to dig more into this. So maybe there's some changes in alpha element abundances affecting planet occurrence in these regions of the galaxy. Maybe what we're picking up is just some proxy for stellar age, right? As you move away from the midplane, you're finding older stars. Maybe that's really what we're picking up. Maybe there's some modification to the stellar disk composition. And possibly, maybe there's some galactic dynamics at play that is affecting this higher midplane population rather than the lower one. My personal favorite pet theory is this idea of system evolution and stellar age. So I think we can rectify two findings here. As I talked about earlier, multiplicity seems to decrease as you get into the thick disk. And one way to imagine that is these are older stars born out of very dense globular clusters. And so what could happen is you have a bunch of planets like you would in any other Kepler-like system. And you have some unobserved distant giant as well in the system. When you're born in this densely packed region, what can happen is these stars can pass by and perturb this distant giant, then leading to a lot of instability in the system and potentially kicking out planets and causing what we're seeing as a dearth of planet occurrence in these older high galactic scale height systems. But overall, the big takeaway here is that planet occurrence appears to be address dependent. While I did say that we're finding consistency with K2 and Kepler, there are some clear differences, some nuanced differences when we look really closely at the data. So I want to think about future work, and there's a lot of people working on looking at younger planet or younger stars because they really give us a snapshot of how planet formation is occurring in the moment right now. And I think there's a lot of good science to be done looking at these younger planets. But I also want to kind of bring up this idea of looking at the oldest stars as well. I think there's a lot of information we can learn there. So what I'm plotting here is a histogram essentially of the stellar age of the planets hosts we know about today. And so you see the average is about 5 gigayears old, but we do have planet hosts that go all the way back to about 13 gigayears. And that's right around when the Milky Way was born. So when the Milky Way was born, we know very early on planets were forming. And we have evidence of this with this pulsar, PSR B1620-26b. Essentially, this thing was born right around when the Milky Way was born. So we know that we had planets really early stages of the Milky Way. And maybe those planets were unique in some form compared to the ones that are around today. So shortly after, or not shortly, a few gigayears after the Milky Way forms, halo stars form as well. And again, we have planets that are roughly as old as that population. 9 gigayears, the thick disk stars start to form. So this is the era of heightened alpha element abundance. So during this period, type 2 supernovas dominate. So we don't have the iron abundances that we see in our current population we see now is mostly alpha element enhanced. So maybe we can learn something about how alpha elements play into planet occurrence and formation by looking at these older populations. And then at 6 gigayears ago, the thin disk forms. And so at this point, type 1a supernovas kick on, and we start to see this higher iron abundance become dominant in the stellar spectra. So by looking at these different populations, we can hopefully learn something about how galactic influences play into planet formation and potentially understand where we come from. Because remember, the solar system was not born today. It was born in the distant past. So maybe the planet formation we're seeing today is different than the planet formation that occurred 5 billion years ago. That's something we want to think about when we understand how unique our solar system is. So the takeaway is that the oldest planets provide us insight into the impact the galaxy has on planet formation. And hopefully by putting all these pieces together in some demographic way, we can understand the impact of planet formation or the impact of galactic influences on planet formation and get a better understanding of where we come from. So in summary, today we talked about the K2 homogeneous catalog of planets and our ability to now dig into this with our measurements of completeness. We talked about how the K2 field seems to indicate that planet occurrence overall in broad strokes is fairly, the K2 and Kepler populations are fairly representative of the local galaxy. And then I concluded today by talking about this interesting trend we're seeing in planet occurrence as you move away from the galactic midplane. And it seems to indicate that planet occurrence goes down as we move up, indicating some unique galactic influence on planet formation. So I thank you guys for listening, and I'll conclude with that and take any questions you may have.
Thank you, John. That's a lot of cool questions, a lot of cool things to think about. And it looks like we have, please raise your hand if you have questions. I have a ton of questions, but I will stay till the end and not take up time. Vlad, I see you have a question.
Yes. Hello, John. Thanks for a very interesting talk. And so you talked about the third possible parameter. And I just want to comment on it. So the one, maybe it's not the galactic influence, but the planet hosting star influence. The idea is that, you know, that when we're talking about the planet formation, for planet formation, you need ionization in the disk, and ionization in the disk comes from the, you know, ionizing radiation from the star, from the pre-main sequence star. And so in the form of X-ray emission and the particle emission, that basically creates the condition for the magnetorotational instability, which is one of the major criterion for the planet formation. So so we come to the point that the metallicity actually affects the level of magnetic activity. So the recent statistics of 3,000 stars show that the stars with the low metallicity have much low magnetic activity, and it can be understood in terms of the, you know, the convection zone efficiency producing the magnetic fields. So this might be another factor, the third factor that may explain this, you know, the correlations.
Gotcha. So you're saying metallicity is maybe just a proxy for the magnetic field activity.
Exactly. Yeah.
Okay.
It is now clear from statistical point of view for planet hosting stars of different ages. So, and also from theoretical point of view.
Yeah, that is really interesting. So that could certainly explain. Yeah, that's an interesting point. I'll have to think about that more. So do you think that that could describe this strange deficit we're seeing as we move away from the midplane because it's like an older population?
Exactly, right.
Gotcha.
Yeah.
Okay.
So as we move away, so we get the low metallicity. Low metallicity drives low magnetic activity. Low magnetic activity drives much lower probability to form planets because of the lower ionization in the disk.
That's interesting. I'll have to think about that some more. Yeah, that's a good point. Thank you.
Thanks, Vlad. I think Alex, you have your hand up next.
Hi, John. Good talk.
Thanks.
So you found a lower planet occurrence rate around higher mass stars?
Yeah, that is true.
Yeah. Okay. So my first reaction to that is that a 3-day orbit, for example, around an M dwarf is not equal to a 3-day orbit around a G dwarf. And just as a 0th order effect, it occurs to me that dynamical temperature could be important. So have you looked at occurrence rates versus orbital energy?
You know, I personally have not done that. I will note that this plot in particular, which was done by Heiss Mulders, it's not period, it's actually semi-major axis, which maybe is a better proxy kind of to what you're saying. I am not sure about that aspect though, but definitely there's been a lot of work on this to verify this since 2012. I'm not the first person to note this, so this is definitely not my discovery by any means. But yeah, that's an interesting point. So you're saying M dwarfs may have a increased occurrence because they have higher energy. Is that true at the same period?
Lower energy, I think.
Lower energy.
Or actually, I'm not sure now.
Okay. That's an interesting point, though. I'd have to think about the orbital energy aspect of that. Interesting. Yeah, thanks for bringing that up. Think about that more.
Yeah, I mean, just intuitively, you can imagine if you're closer to like a Roche limit or something like that, that's probably there's probably scattering that's heavily influenced by kind of how compact you are. I know you have a bunch of cool studies on compactness too. How many planets you might have in and around the habitable zone. I'll ask about that later. Before I ask about that though, on the galactic question, so for the planet hosting stars that have been observed, how much clumping is there in terms of we've mostly observed in things that are pretty close to each other in the thick disk as opposed to the thin disk? How much would you benefit from an isotropic analysis of certain?
Yeah, that's a really good point. I mean, we're definitely limited to the K2 fields that were kind of looked at. So there's probably a significant amount of clumping based on that. I'm not sure it's a huge impact, but it certainly could play into what we're seeing. So maybe there's certain regions that are kind of asymmetric and possibly causing this. I would say this trend is pretty strong, especially for the sub-Neptunes. So I'd be surprised if it's just a clumping issue, but it's definitely something that could be benefited by maybe TESS follow-up. The only problem with TESS is that it's really challenging to get longer period stuff. And we don't quite get the depth because we can't quite get the dimmer stars with TESS. So certainly something to think about though, moving forward as we get more and more TESS data built up.
Gotcha. Avi?
Hey, yeah, great talk, John. Really nice. Really, first of all, great graphics, really well described. Beautiful talk overall. In terms of, obviously we talk a lot about this less than 10 or less than 20 day demographics here, but it also seems like we're getting a much better handle on, say, the 20 to 40 day demographics, especially after all of the hard work that you guys and all Kepler and K2 teams have done. Where obviously, things like photoevaporation, other things like this stop, being as confounding, and maybe formation plays a more, or imprints more directly. I don't know if you can say, or we can say anything about these things you're talking about, you're showing here, and what that is sort of suggesting about formation processes going on there.
Yeah, so I think what you're saying is maybe there's more in situ formation occurring at these larger orbital periods, or maybe it's not so much of an effect of the stellar ionization or anything like that. That's certainly true. I'm actually working on a paper right now thinking about, as you move outward, is there a break in the outer disk edge as well? So we've talked a lot about this inner disk edge, but there's some evidence with Kepler that we're actually seeing a break on the outer end too, because we get out to longer periods, we're finding, which is not really illustrated nicely here, but at some point, it appears that planet occurrence actually turns over at about 100 or 200 days as well, indicating maybe an outer edge of the disk. So yeah, there's a lot of work being done in that mid-range, which I think is really interesting too. I don't have a good kind of explanation for why things are happening there though.
Okay, thanks.
So let's see, do we have any other questions? Otherwise, I will ask something about not quite related to these three, but kind of related to the work you've been doing. So some of the earlier
Sorry, hold on one second. Sorry, I apologize.
No
I'll
worries.
really quick here. Yeah, what was that?
So yeah, so those early graphs you showed, which kind of looked at occurrence rate, and one of the things that I noticed was that you had, it wasn't totally complete, but you actually got completeness below the 1 Earth radii size. So how well do you do on sub-Earths in some of these things? That's pretty exciting to me as I think about populations and kind of demographics too.
Yeah, so we do fairly decent on the sub-Earth range at very short periods, just because you can kind of amp up the signal with more and more transits. As you get out to, beyond 10 days, it gets really hard to find anything that's sub-Earth in both Kepler and K2. It's very challenging. Yeah, it's really interesting. I'm not sure there's been a lot of analysis, of the below Earth planets. Thinking
Because,
about that.
one of the things I think you see often is, this idea of closely packed, peas in a pod planets and around M's. And, at some point, yeah, I think about our solar system, and we have some relatively closely packed peas and pods in the inner solar system. So where do you start to see that break? Where do you start to see, is that still kind of true as you get to different stellar classes, all this other stuff? That's interesting because it has impacts on, habitability and a lot of those questions too. But no, really cool stuff. Let's see, any other questions? If not, thank you again, Jon. Obviously, there's a lot of questions, a lot of interest in all the 3 sections you had. So I hope to, excited for these future papers and the other stuff you'll be working on too.
Great. Thanks. Thank you, everyone, for listening. I appreciate your time.
Thanks a lot. Bye.